Okay, so as I mentioned, here we go with our friend Chem 50, which, as we talked about, you should have took and should have passed, hopefully. Perhaps don't let me know if you didn't, I suppose. So in Chem 50 was the first semester general chemistry. It also covered very similar stuff to what you talked about in Chem 40. There are certain things from that class that you will sort of use in this particular class, both in the lab portion and then also in the lecture portion. So we're going to cover up front here some of the earlier stuff like taking measurements properly and sig figs, just to make sure everybody's on the same page. Obviously, you'll need that when we're doing labs and obviously homework and stuff like that. And we'll talk about some reactions, and we'll talk about solutions. Which are things that we definitely sort of come across in this class. All right, so might start at the beginning, which is basically measurements, which will serve you in every class, including this one. So when we do take measurements, right? By the way, there's no handout for this one, just going off the top of my head, just so you know. When we take any type of measurement, there's always some degree of uncertainty with a measurement. And the degree of uncertainty really lies with what piece of equipment that you use. That's why whenever you're, for example, in a laboratory, you should always look at the piece of equipment that you're using. You should always sort of try to figure out what does the scaling mean on that piece of equipment and really how far you should take the reading to. You definitely in our lab, like any other lab that you take, when you take measurements and stuff like that and readings, you want to always make sure you take them to the proper number of digits. In addition, before that, right, any measurement really should have a number and a unit associated with it, right? So, if you just write 255, what am I talking about? Who knows, really, right? I hope personally I'm talking about $255. That would be great. But maybe I'm talking about 255 pennies, maybe 255 apples, which would still be great, I suppose. So numbers by themselves are not useful. That unit part is really useful. And as you may know, there's really two types of units, right? There's the English units, and that's pretty much what we use here in the US. And there is the metric system, which is pretty much what everybody else uses in the world. And in 1960, they sort of came together in terms of units for sciences and came up with is sometimes referred to as the SI system of units. And that's the International System of Units. And it really is, for all intents and purposes, the metric system pretty much is what that is. And we pretty much use that a lot in chemistry, obviously. With the metric system, as you might be aware of as well, there are like prefixes, right, that we sometimes use, like kilo, centi, and stuff like that. For example, kilo, right, is 10 to the 3, which is 1 times 10 to the 3. And just to make sure everybody knows how to properly use a prefix like this, when you see something like that, if I am going from kilograms to grams, in 1 kilogram, right, which is the prefix unit, there is 10 to the 3 grams, which is the base unit, right? The base unit here, right, is grams in both of them, right? So I can't tell you how often people do that backwards. They go 10 to the 3 kilograms in 1 gram. So when you see that little prefix chart, or go to reference it, when you see that 10 to the 3, 10 to the minus 2, whatever it may be, that's how much there is in the base unit to one of the prefix units. So it's really important that you get that sort of correct. Again, it's a very common mistake that people make as well. Like centi, right, is 10 to the minus 2. That means that if I have centimeters and meters in 1 centimeter, right, there is 10 to the minus 2 meters. That again is the proper way to do that. By the way, if I divide 10 to the minus 2 to both sides, I get another conversion, which is the same, which is 100 centimeters is 1 meter, right? So same deal, right? If you go that way with it as well. So make sure, obviously, you always include a unit with whatever you write, especially in lab, especially in here, and also in calculations. You should make sure that you always have units associated with it. So getting back to measurements, whenever we take a measurement, let's just say we got something like this, a ruler. All these centimeters. And if we wanted to measure, say, this line here, we'll go somewhere like that. Usually on whatever scale that you look at, right, you want to basically determine two things. There usually is larger markings and smaller markings, or major and minor markings. In this particular case, our large markings usually will have numbers. So that's a 1, that's a 2. So our large marking represents 1 centimeter in this case, right? You also usually want to count how many small markings you have between the two large markings. And when you count, you always start after the large marking. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that is 10 markings between 1 centimeter. That means each of the small markings represents how much? 0.1 centimeters, right? So that is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, all the way up to 2 in that particular case. So when you do take a measurement, you should always have numbers that pretty much no matter who takes a look at it, everybody should agree that those are the correct numbers. So in this example here, no matter who looks at it, everybody should agree it is at least 1.3. These are what are sometimes referred to as certain numbers. But we could clearly see that it's not exactly at 1.3, not exactly at 1.4 either. And that is where the uncertainty comes in a measurement, or the estimation that is sometimes referred to. So I may look at it and go, well, I think it's a little bit more than half. So maybe it's like a 6. And then I obviously would record my units with that. This would be what is referred to sometimes as the first uncertain number. When you take a measurement, you should always record all the certain numbers plus the very first uncertain number. And that is because those things all together make up what? Yeah, that is basically what significant figures are, right? So these are significant figures, which means my measurement here would have 3 significant figures in this case. The uncertainty would lie in the last digit there, which is the 6. So a lot of times we think of it as being plus or minus 1 of that last digit. You could also take the smallest markings divided by 2. And if you divide it by 2, it gets you 0.05, kind of plus or minus 0.05 for the precision there of the equipment. It also will tell you clearly that is 2 decimal places. That is pretty much what my reading should be. So sometimes people will write something like 1.36 centimeters plus or minus 0.005 centimeters. I don't need you to do that, but sometimes people do that. Although it is technically plus or minus 0.05, usually you take a pretty better reading. So it probably would be more so plus or minus 1 of that last number is kind of where you typically will see that error. And it's important to always look at any piece of equipment that you use. Some award-winning drawing. Probably why I failed art 9 times. All right. I stopped before the 10th time. So that is 10. That is 20. Call that milliliters here. We'll put a little volume action in there. Fill it up with something. We'll go with blue Gatorade here. Go. As you know, right, when you put a liquid in something like a glass cylinder, we get the curvature of liquid, right, known as the meniscus, right? And we always read from the badly drawn bottom of the meniscus there. Meniscus occurs because the attractive forces right between the liquid and the glass container are actually stronger than the liquid in itself. So through capillary action, the liquid on the sides, which are in contact with the container, starts to rise up the side of the container there. And that's why we read from the bottom of the meniscus, because without that attractive force, the true volume is what we see in the middle, basically on the bottom, right? That's not in contact. That's really, if they didn't have that attractive force, they would come back down to that level. And that's why we look at the meniscus when we take a reading. Also, it is sometimes easier to see the U meniscus, if you will. Sometimes a little bit harder to see it depending on the piece of glassware that you use. That's why we don't use wide open beakers to measure things, because it's pretty wide open, which means the meniscus gets spread out, which means beakers are crappy things to use to measure things out like volumes, right? It's very hard sometimes to see the meniscus, rather than say a graduate cylinder has a little bit narrower, a little easier to kind of see the meniscus. Probably 99% of the time, the meniscus will look like that, the U-shape, right? But there are certain substances that actually can go the other way, can make the meniscus go more of an end situation like that. And in this situation, you would actually read from the top of the meniscus, because what's happening here is the attractive forces between the solution and itself, it's actually greater than that of the container. And it actually folds in on itself rather than goes up the walls of the container. So again, without that attractive force, it would actually be at the top of the meniscus. We don't come across it too much because they pretty much have removed mercury from a lot of places. But mercury is an example of something that actually does that. If you ever see old barometers that are filled with mercury, you could actually see that the mercury actually goes in the opposite direction because of that. But probably 99 times out of 100, it's going to do the kind of U meniscus when you do it. So we would still want to do our proper sort of look here. Big or large difference here is 10 milliliters. There is, again, starting here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings, which means in this case, each of the smaller markings is 1 milliliter, right? That's 11, that's a 12, 13, 14, 15, 16, and 17. So once again here, if we look at it and look at our meniscus, which would be somewhere in that ballpark, we would agree that it's at least 16. That would be our certain numbers there. The estimate, maybe here you do feel it is sort of in the middle, and maybe record a 5 and milliliters. And again, that would be our first uncertain number. And that would mean, again, in this case, this has 3 significant figures, right? Now, it's important to take a reading of everything and look at the scaling, because things change. Even if you're both using, say, the same 10 milliliter graduated cylinder, it's made by different people, it may actually be different in terms of how the scaling is. So let's say we had something like this. And that. And we'll throw it right about there. So once again, if we look at our large distribution here, our large marking is 10 milliliters. In this case, when we count up the smaller markings, in this case, that's 1, 2, 3, 4, and 5 markings in this case. That means each of the smaller markings represents how much in this case? Each of the smaller markings represent 2 milliliters, right? That would be 12, 14, 16, 18. So now when we go to take our reading, our meniscus there is between 14 and 16. Between 14 and 16 is 15. Yeah, so that would be 15 milliliters in this case. That would be the best that you could do. That means that this number would have how many significant figures? It would be 2 significant figures. The uncertain number is 5. Yeah, so we're actually saying I think it's 15, but maybe it's 16 or 14 in that particular case. So it is important to look at the scaling. In general, you can go usually one more place to the right of the smallest marking. That's not really the case here. If you're ever unsure of how far you should take a reading, but you can't figure out what the smallest markings mean, Again, you could just divide it by 2 and it'll tell you how far to take it. So if you take this guy over here on the left and divide it by 2, that's 0.5 milliliters, which is 1 decimal place, which is where you should take the reading to. Even if you take this guy, which is 2 milliliters divided by 2 is 1 milliliter, which is a whole number, and that is where you took this to. So if you're unsure, but you can still figure out what the little markings mean, divided by 2, and that's really how far you should take your reading to do it correctly. Any questions on that there? Yeah. We also use a burette a lot in this class, and you use it for titrations. You also want to make sure you understand how to read things properly. So when you have a burette, which is wonderfully drawn just like that, at the top there is 0. That is a 1. That is a 2. That is a 3. That is a 4, and so forth. When you fill a burette, you put the liquid in on top, right? It comes out the bottom when you're doing titration. So if you find yourself in this region, what is the volume if these are like milliliters? Is it 2 point something or 3 point something? It is 2 point something, right? Probably 2 decimal places usually on a burette is how far you take it, but it is 2 point something. It does increase. By the way, if I fill a burette all the way up to the 0 mark, and let's just say that this is a 50 milliliter burette, do I mark 50 or 0? You fill it up to the top, and you're going to take a volume reading. You should record 0. Yes. So whenever you use a burette, you should always record the. Well, when you use a burette, you have to record the initial volume, right, and the final volume, right, and you subtract it 2, and that'll tell you how much you delivered. So you should always record on a burette the exact number it's at, not the total volume. Because if you record this at 50 and then you record where it ends up, you subtract that. That's not how much you put in there, right? So you should always record exactly what it says. So if you started the titration at 0, 0.00 milliliters would be your initial volume. Let's say you drained it down to here, which would be something like 2.50 milliliters, right? Which would be your final volume. The volume you delivered, final minus initial, right? So that would tell you put in there 2.50. That's important because what happens if you didn't start at 0, but you started at, say, 0.10 milliliters, right? And you went down to 2.5 milliliters. Did I put in there 2.5 milliliters? I did not. I put in there 2.4. Yeah, so I put in 2.4 in this case, right? So you always want to, and it's a super common wrong thing to do, is people, when they fill a burette to the top, they record 50 or 25 or however big it is. But you should always record the actual volume reading that you see on a burette, and you should always record the initial and the final reading so that you can subtract it to and figure out how much you actually added to it. Yeah. Any questions on that? Yeah. Okay. And in general, on most burettes you probably will use, like I said, if you look at the scaling, you'll see that there's usually 10 little markings between the big markings, and usually the big markings is 1 milliliter, which means each of the smaller markings is like 0.1 milliliters, and you could then take it again one more place to the right, which is 2 decimal places is typically what we do. We're going to do a lot of titrations come in the middle of the semester, yes, so we will use a burette a lot. So for your own sake, make sure you do take proper readings. As you also know, if you don't take the initial and the final reading while you're doing your titration, you pretty much waste your time, yes, because you don't know how much you put in there, right? So you got to always make sure you do that. Any questions on any of that measurement stuff? Yeah. Now, when we talk about measurements and taking things, there's qualitative and there's quantitative type of measurements. Qualitative is more just sort of general observations. So usually when we do experiments, we take a lot of qualitative type of observations. You know, it turned red, there's a solid, there was rainbow and unicorns that came through the class, whatever it may be, you know, you want to record those things. As opposed to also we take quantitative, which are basically measurements, which are values and units and values. Now, there is actually a whole area of chemistry experiments where we do it more qualitative. It's called experiments which are qualitative analysis, which we used to do in this class all the time. And again, that was the one I said you should be happy you don't do anymore, because it's usually really smelly type sulfur containing stuff that she has to play with. But in like qualitative analysis, which are very common experiments that you do in second semester general chemistry at some places still, it's all about not really measuring. So even we could do experiments where if it's not so crucial that you get a certain volume of something and you miss it by 1 drop or 2 drops, it doesn't really make that big of a difference. We do those things. So like in qualitative analysis, you never measure out anything. You just go like, hey, 40 drops is a milliliter, and again, if you put a little bit more or a little bit less, it's not going to make a tremendous difference. We don't measure out anything like on a balance. If you need a solid, you just take like a little scoop of it and kind of put it in. And there's a whole bunch of experiments where we do it really qualitative. For our purposes here in this class, for most things that you do experiments is more quantitative. You want to make sure you take measurements to the proper numbers, you get the right units and that stuff. But it's also really important to make sure you still do the qualitative part of it, right? So as you're going through experiments, you don't want to just be focused on writing down all the numbers, but if something happens visually, right, that's not a number, but some type of observation, you should have those things in there. Like it started to bubble, right? A solid, a precipitate was formed. My experiment blew up in my test tube. One of those things, though hopefully that doesn't happen, but you want to make sure that you record those type of information. Speaking of significant figures, just to make sure, right, when we talk about sig figs, any non-zero number, right, is significant. When we talk about zeros, that would mean obviously something like 1, 2, 4, 5. That would have 4 significant figures. We always start counting on the left there, right? At the very first non-zero is where you want to start counting your significant figures. In terms of zeros, there are a couple of different types of zeros. There are leading zeros. And these are not significant. So if you have 0.0000123, none of these are significant. We don't start counting until we hit the 1 here. And then we would have 1, 2, 3, which would be 3 significant figures in this case. There's also kind of trap zeros or captive zeros is sometimes referred to. And those are significant. So if you have something like 4004, we would start counting here as that's a non-zero. These are trapped between 2 non-zero numbers, which means that this has 4 significant figures in this particular case. The last type of zero that really gives people a lot of trouble is the zero that comes at the end. So that is sometimes referred to as trailing zeros. And they may or may not be significant. What determines whether or not they're significant is a decimal point. So if there is a decimal point in the number, then they are significant. So if I had something like 600 written like that, how many significant figures does it have? It does have 1. The 6 here would be significant. These are not going to be significant because there is not a decimal point actually written, although we sometimes assume it's at the end. It does need to be written when you're counting significant figures. So if you do not see it, it is not there. So this would have 1 significant figure. If I wrote 600 like this has how many? Does have 4. That's significant. And all these zeros are significant because of the decimal point that's there, which would be 4 significant figures. When you write a number, say that is a small number like this, you should get in the habit, if you don't do so, right, write the 0 in front of the decimal so that not all the numbers blend together as you're doing calculations. So there's some type of distinction between them. By the way, that would have how many significant figures? 3. And now it would have 7. So again, these are not significant. I think it's 7. We would start counting here. So all 3 of these are significant. That's significant as 4. That's significant. These are significant because way over here, right, there is a decimal point. So all those numbers at the end would be significant. The uncertain number, right? For example, if we have 12,000 here, how many significant figures are there? The uncertain number is which number? It is the 2, yeah. So when you're asked about the uncertain number, estimated digit is not always the last one written, but it should always be the last significant figure written. So in a lot of cases, it actually is the last number written, but it won't always be necessarily. It will be in that last significant figure. Now, when we talk about rounding, right, it's important to round correctly as well. Say I had, we'll do this, 13,333. And I want to do 2 significant figures here. What should the answer be? 13,000, which one? Yeah, it should be 13,000. This has 2 significant figures, right? That has 2 significant figures. If I owed you $13,333 instead, I'm just going to give you 2 sig figs. Here's $13. Probably not going to make it out, right? There's a big difference between 13 and the value 13,333. So that's no good. But maybe if I give you 13,000, you give me the $333 teacher discount, we'll still be okay. It's about the same thing. So in the effort of getting the right number of significant figures, you should not go extreme rounding, yes, or anything like that. Speaking of extreme rounding, a little bit about measurements and significant figures. Let's say we had that same sort of scale that we were looking at originally, which is 1. 2. When you do measurements, for example, let's just go right dead on to that guy right there. So earlier we saw in this situation, our large markings was 1 centimeter. Our small marking here was 0.1 centimeter. So that means, again, that's 1.1, 1.2, 1.3, 1.4. So we feel it's like dead on that 1.3 line, right? So I record 1.3 centimeters. I record 1.30 centimeters. I record 1.3000000000 centimeters. I feel like that's a lot of zeros, so I'm just going to cross that one out. By the way, don't add a bunch of zeros to make it look more chemistry-like, right? It just looks a lot of zeros in that case, right? So is there a difference between those 2 measurements? There is a difference, right, between those 2 measurements. When we look at this measurement here, that is 2 significant figures, right? Which means the uncertain number there is the 3. You're basically saying, I think this measurement is 1.3, but maybe it's like 1.4 or 1.2. That's a pretty big range of error, yes, between those 2. Now, really on this, when you look at this, this has 3 significant figures, right? The uncertain number being that 0 that is present right there. And what you're saying here is, I think it's 1.3, but maybe it's like 1.31 or 1.29, which is pretty much in that region, right? Which is what we actually do see on this particular equipment. So sometimes people think, I could just lop off a number or something like that, or a significant figure. There is a big difference, right? If I made the measurement there, like on the left, it's a much crappier measurement, right, than the one on the right. There's a lot more error associated with it. So we don't want to do that. So you should never lop off things, even if it's dead on a number. You should add a 0 if you need to maintain the proper number of significant figures. And you should not add too many zeros, because it's just as bad going the other way, because the other way there would say I would have a ton of significant figures, right? I'm not quite sure what piece of equipment I'm using to measure that with, but I don't have that equipment either, right? So you want to make sure that you do give it to the right number of digits, and in this case, it should be that. That also goes for things that are digital. That's a very common thing, like when people go weigh out something on the balance, they just lose some numbers. So in general, if it's digital, the numbers are important, otherwise they would not be there. So you should record all of the numbers that you see on a digital display, because they are all sort of important. Any questions on that there? Speaking of significant figures, right, just to review calculations, right, with sig figs, we basically multiply or divide, right? Or we add and subtract, right? It's basically the 2 sort of big things that we do. When we multiply or divide, the answer should have the same number of significant figures as the number with the least number of sig figs. When we add and subtract, the answer should have the same number of decimal places as the number with the least number of decimal places. So one case we look at sig figs, one case we look at decimal places. They are both the least because that is your worst measurement, frankly, in that group. And your overall calculation is only as good as your worst measurement, pretty much. So for doing like 4.25 times 1.2, that is 3 sig figs, that is 2 sig figs. Answer should have 2 sig figs. For adding 1.11 plus 2.0, that gives us 3.11. That is 1 decimal place. That is 2 decimal places. Answer should have 1 decimal place, which is 3.1. 3.1 has 1 decimal place, but only how many significant figures? 2 significant figures. Those are 2 different things. Yes. If you're doing a bunch of calculations in a row, yes. Like maybe you are multiplying first, and then you are dividing. You typically do the guy in the parentheses first, which means that is 3 significant figures and 4 significant figures, which means my answer up on top technically should be 3 significant figures, which I'm then going to divide by 2 significant figures on the bottom, which means my answer should end up at 2 significant figures when it's all said and done. You should avoid rounding right to the very end, especially if you're going to do multiple calculations in a row. You should take the answer to a few digits and then really clean it up at the end. So you should keep track of everything and clean up all the sig figs at the end. You don't want to do a lot of rounding along the way because every time you round, you're kind of moving yourself further and further from the correct answer. So you will probably get it incorrect. Any questions on calculations? Yeah. So in addition, when we do take sort of measurements and that type of stuff, we talk about 2 things, which is being accuracy and precision. So being accurate or being precise, there is a difference. Accuracy or being accurate is how close you are to the true value. Being precise or precision looks at how close a set of numbers are to one another. Right. So if we do the classic bullseye example, right? We got like a bullseye, we're going to throw some darts at it. Goal is to hit the bullseye. I throw my darts the first time, I hit here, maybe I missed the board. Ooh, bad throw. Am I precise? Am I accurate? Probably shouldn't have picked up the darts, really. So we're going to go double or nothing in a friendly, non-wager type thing. And we're going to pick up our darts. We're going to throw them again, right? And if I throw them again, am I accurate? Am I precise? I'm precisely not accurate, right? And that illustrates a really good point. You could have great precision. You could do the thing crappily and wrong every time the same way, and you'll get the same result every time, but it's wrong, right? So you can be very precise, but not very accurate, right? And so it is possible to be very precise, but not very accurate. So we go triple or nothing here, and obviously I throw my darts because clearly I've been hustling you the whole time here. And am I accurate at this point? Am I precise? And that's usually what we're shooting for, right, in chemistry, is to be both accurate and precise when we do experiments, right? We want to be close to what the true answer should be. And what we look at in terms of precision is why we really do a lot of times multiple trials, right, in experiments, right? We do multiple trials to see if our procedure is reproducible, right? That we get the same answer every time. So in experiments and stuff like that, when you do multiple trials and you get like the same answer every time or very close to the same answer. It's very reproducible. It has good precision, right? Which is what you're looking for. We also do things for accuracy as well, right? That's why we calculate things like percent error, right? Percent error deals with which one, accuracy or precision? It is accuracy, right? You take basically the experimental value minus the true value divided by the true value times 100. So we look at accuracy through percent error. We want a low or high percent error. We do want a low percent error, right? You can't get like, I got 200% error. I did it 200 times as wrong as everybody else. We look at percent error for that. For something like precision, we look at standard deviation, percent deviation. And again, that's why we oftentimes will do multiple trials, right? To kind of see, is it reproducible, those type of experiments. Any questions on that there? All right. So our other favorite thing, right, is our friend scientific notation. And scientific notation properly written has this format, n times 10 to the n, where that is a number between 1 and 10. That means not 10, but between 1 and 10, 1's okay. But not 10, not 20, not 100. That also means when you write in scientific notation, it should not be point something of a number, right? It needs to be between 1 and 10. This number is a positive or negative, depending on which way, obviously, that you move the decimal to do that. So if we had 1, 3, 5, 6, we would go 1 place, 2 places, 3 places, 1.356 times 10 to the 3. We had a number like this, 0.002567. We go 1, 2, and 3 places, gives me 2.567 times 10 to the minus 3. Large numbers, right, have positive exponents, right? Smaller numbers have negative exponents. If you move it to the right, that is going to be a negative exponent. If you're turning it into scientific notation, if you move to the left, turn it into scientific notation, it will be a positive number. Why did I keep all the numbers on both of those? Yeah, so when you write a number in scientific notation, all the numbers that come before the times 10 part, right, are significant. So you should never lose significant figures as you go from scientific notation to decimal form, or positional notation is sometimes referred to. So that's why we have to keep all those numbers when we do it. Now, more importantly, probably is that most people don't know how to properly punch into their calculator scientific notation. So let's make sure you properly know how to do that. On most people's calculators, you actually have a exponent button, and on most of them, it will either be an EE button, it will be an EXP button, and on some of the new fancier ones, I guess they're not new, they've been making them a while now, you have a times 10 to the n button. Usually on those calculators, you will also have a will on your calculator that looks something like that. So if you have this button, we'll talk about you in just a second. And if you have those buttons, those are really your exponent buttons when you are going to punch something into scientific notation into your calculator. Also other buttons, negative buttons, usually look like this, positive, negative, or something like that. You should not use the subtract button, right? When you're punching something in that has a negative exponent. So when you go to do that, if you want to type something like 6.25 times 10 to the minus 6 into your calculator, proper way to do that is 6.25. You should hit your exponent button, either one of those. And on most displays, it'll go 6.25 and pop up an E. May go 6.25, maybe we do a little 10, and a couple of zeros might pop up on your display. When you hit the EE button or EXP button, it represents the times 10 part, which means you should not hit the multiplication button. You should just hit that button. That is it. What is left is negative, which means you should take your negative button, whichever one you got, hit it. That'll be that, that'll be that, and 6. 6 and 6, yes. And that is the proper way to punch it in as scientific notation into your calculator. You should not use the multiplication button when you're just punching in one number in scientific notation. You should not use the inverse log button, because that is the incorrect way of doing it. You should not use the shift log or any of those things. So if you're using any of those things to punch it into your calculator, you are doing it incorrectly, and you're going to be in a world of trouble in a few chapters down the road here, or a couple of chapters down the road. So you want to make sure that you definitely do punch it in correctly. A reminder that your calculator will not necessarily give it to you in scientific notation unless you have it set to do so. It may in certain cases, and it may not in other cases. Do you have to give your answers in scientific notation all the time? The answer is no, unless it says to do so. But there are certain times when the only way to give the correct answer, the correct number of significant figures, is to write in scientific notation, because you could really control how many significant figures you put there. Now, if you have these two buttons, you really don't have to worry about too much when you punch it in scientific notation. If you have one of these other calculators that has this type of button, and a lot of times they're like two-tone type color calculators, like a main color, and then the sides are slightly different. You kind of have to do the same thing, except because of the way those calculators are usually programmed, you got to lay up some parentheses around them, each of the numbers that are in scientific notation. So you need to open a parentheses to start, then the rest is pretty similar, 6.25. You hit your times 10 to the n. At that point, it will look on your screen something like this, 6.25. It'll pop at times 10, and you'll have a little blinking cursor right about there up on top. At that point, you do the rest of it. You can do your negative button and 6, and it will turn your thing into 6.25 times 10 to the minus 6. And now you'll have your blinking cursor still up on top. You have to actually close your parentheses for your calculator to do the calculation. And if you just close the parentheses with the cursor all the way up there on top, it will close it up here. And in most calculations, you'll get an error because it's like up there, it shouldn't be there. Not good. So what you actually have to do in that situation on those calculators is, that is where the wheel comes into play. You just hit that there on that side, and that will bring your cursor back down to normal. And then you can have something that looks like this, and now you can close that parentheses, and then you'll be in good shape in that. So if you do have that button, you do have to put every number in parentheses if you wanted to do it correctly. If you have the other two buttons, pretty much you don't have to be that careful at all. You just hit it, and it's usually good on most calculators. Any questions on that? So probably more important than writing in scientific notation is to properly put the number into your calculator. If you find yourself doing some type of problem, and usually if you get an answer like, say, 7.11 times 10 to the minus 22, if this part of the number is all good, but this part is just slightly off, it is probably how you are punching it into your calculator when you're done with it. If you're not sure where your exponent button is, you should go and see me at some point. Not go, I'm just kidding. You should come see me at some point. We'll figure it out on your calculator. But those are really the common sort of exponent buttons that you want to make sure that you use. Any questions on that there? Other common things that people don't know how to use calculators for, let's say you have a lot of numbers you're going to multiply, and then you want to take some numbers here on the bottom, and you got a bunch of numbers. Don't really matter what the numbers are. Or maybe you're going to add a bunch of numbers on top. So sometimes people want to punch all this into their calculator all at once, and if you don't know what you're doing, like you should be using some parentheses there, and you don't do it properly, you will get the wrong answer. So it's very advisable if you're going to do a bunch of numbers that maybe it has to divide by a couple numbers or a few numbers. You can do as much as you want on the top part there. You can multiply as many numbers you want, add as many numbers you want, subtract as many numbers you want. But at the end of doing the top part of the calculation, I highly recommend you hit equals. And then you should divide by the first number, and then you should hit equals. Then you should divide by the second number and then hit equals, and you will always get the right answer. You try to punch it all in at once, probably gonna get the wrong answer. So that's a super common error that people make, is they try to punch everything into their calculators all at once, and they go, I don't understand, I punched in everything just like you. So it's sometimes better to do it individually, hit that equal sign. That way your calculator for sure knows what it's supposed to do math-wise, depending on how it's programmed. If you shove everything in there at once, it may not do the calculation you think it's doing. Any questions on calculator, scientific notation, any of that stuff there? Okay, so let's talk about some other stuff that's important. Things like molar mass, yes? Molar mass has units of grams per mole. We can find the molar mass of things from the periodic table, right? It is found, say, on the bottom. That is the molar mass, also the atomic mass. By the way, the number up on top, right, which is carbon there. That number is that is the atomic number, right? That's the number of protons there are, right, in an atom. Bottom number is not the mass number, right? Mass number is the number of protons and neutrons, right? Not found on the periodic table, by the way. That is the atomic mass, which is the mass in AMU. That's 12.01 atomic mass units per atom, which is equivalent to the molar mass of it, which is 12.01 grams per mole, right? For carbon. We could use that as a conversion factor, 12.01 grams on top, moles on the bottom, are moles per 12.01 grams. When we do calculations in chemistry, we do dimensional analysis, right? Which is how we set up things to show units canceling out. So if I had 45 grams of carbon, I want to know how many moles it is. I would use the molar mass in this version, put the 12.01 grams on the bottom, the moles up on top. This is like fractions, right? Grams of carbon divided by grams of carbon cancel, right? We multiply across the top and divide by whatever's on the bottom, right? So we take 45 times 1 basically divided by 12.01. I end up with 3.746877602 moles of carbon. You clearly would not give me that many numbers, right? I've had people give me that many numbers. They like wrap around to the next side of the page, like on an exam. Too many numbers. Yes, we should look at some sig figs here. Should be how many? Should be 3 based off of that number, right? We're multiplying and dividing. So that's 3 sig figs. That's considered sort of an exact number probably. So we'll go about there. 3.75 moles of carbon. So you should show your work in dimensional analysis, right? Showing the units canceling and set it up that way. By the way, exact numbers are things that are counted, right? Are things that are definitions. Like 1 inch is 2.54 centimeters. Any type of conversion that is a metric to metric conversion or English to English conversion are exact numbers, right? When you cross over from English to metric, are those exact numbers? They're not. You actually should look at the significant figures. I would say probably 9 times out of 10, the most calculations that you do, like that first number is probably the right number, sig figs, but not always. But if you do cross over metric to English, outside of like 1 inch is 2.54 centimeters, you really should look at the significant figures that are involved in that case. Molar mass is a very important conversion that we use to go from grams to moles, right? And moles to grams. And we find that in the periodic table. And that is our conversion factor to do that. If we had something like CO2, we would add up all the parts. There is 12.01 grams per mole from the periodic table for the carbon. We would add it to 2 times 16 grams per mole for the oxygen, giving us 44.01 grams per mole. The molar mass, the grams always gets the number, or the numbers is always the grams per 1 mole. So regardless of what you got going on, that is what you should use. You should never calculate the molar mass of something based on the coefficient in a balanced equation. The molar mass is always calculated from just the formula, right? Just one of the formulas is what you calculate the molar mass from. Our good friend Avogadro's number here, we can't forget him. That is 6.022 times 10 to the 23. These could be atoms, they could be molecules, they could be pizzas, they could be shoes, whatever they may be. But that is what 1 mole equals, right? So we use this to go from really moles to atoms or molecules or backwards, right? We should not always use Avogadro's number in every situation. We should only use it in a situation that mentions something about atoms or molecules. You got to either convert to that or end up in that or start with that. Otherwise, you should leave Avogadro's number on the side there and not really use it too much. Any question on any of those things there? All right, this is also what we use, right? Molar mass, if we want to figure out how many grams of something to weigh out, right? So if we can use the molar mass and we know how many moles of it that we need, we could use it to figure out how many grams we should go weigh out. That brings us to reactions, right? All chemical reactions are a result of what happens in a chemical reaction. What happens? Yeah, there is reactants, right, which is our starting material. And they do go to products, which is what is formed, right? And the only thing that happens in a chemical reaction is bonds are broken, right? All the bonds over here get broken. And over here, bonds get made, right? In a chemical reaction. And bonds breaking and bonds making is all about electrons, right? And that is why we have conservation of our elements, right? Because we don't change anything in the nucleus. Protons, neutrons, they don't get touched with in normal chemical reactions. We'll talk about in nuclear chemistry, that is where they get played with. But in normal chemical reaction, it's just bonds being made and broken, which means we have the conservation of our elements. We have our reactants and our products, starting material, ending material. Other things that we see are symbols, right? Solid, liquid, gas, aqueous. And these are the states of certain things that we see. There is a difference between liquid and aqueous, right? Liquid is a pure liquid, aqueous is a solution, yeah? And usually they're made by taking something like water, which is a pure liquid, right? And if I take something like sodium chloride, which is a solid, and I mix these together, the sodium chloride will dissolve in the water and we will get an aqueous solution or water type solution of sodium chloride, right? Which is a solution. So a aqueous is basically a solution, and something that has the L designation is a pure liquid substance by itself. Other things that we see sometimes in reactions, we see catalyst written up on top of the arrow. So we'll sometimes see things like platinum, maybe H plus, which is a catalyst for an acid. You also will sometimes see the little delta symbol written. That usually means heat, right? When you see it on top of the arrow. Sometimes you may see on top of the arrow water written there, which means you're dissolving something in water. Although a lot of times we use chemical equations to represent chemical reactions, we also can use it to do physical processes like melting an ice cube, right? Where you could have, water on one side, water on the other side, just different states. Clearly, when we deal with equations, they do need to be balanced, right? And when we balance an equation, we only change the coefficients, right? So in this particular case, we need to make sure we have the same number of each of these elements on each side. So in this case, it looks like we might need a 2 there and maybe a 3 there. So we should only change the coefficients in a balanced equation. Sometimes when you balance equation, right, you might have to use a fraction, right? And should you leave the fraction when you balance the equation? You should not. When you're done balancing an equation, all the coefficients should be all whole numbers, and they should be the simplest set of whole numbers that you could have. So if you found a way to balance an equation where you had these numbers as your coefficients, you technically go through all these and divide by 2, and that is what you should do. And that would be really the properly balanced equation. So if you're able to balance equation with larger numbers, but still can reduce everybody down by a whole number, you should do that. Any questions on balancing equations? Remember polyatomic ions, if you have those in equations, sometimes it's easier to keep them together as you're balancing them and just balance them as units. And oftentimes will come a lot quicker when you go to balance them. While we have an equation here, our other favorite thing is with those coefficients is stoichiometry. Yes. That is the mole to mole relationship that we get from the balanced equation. So in this equation, we could say 1 mole of N2 reacts with 3 moles of H2. We can also say 1 mole of N2 will get us 2 moles of NH3. We can also say 3 moles of H2 will get us 2 moles of NH3. This is the mole to mole relationship that we could use to figure out, how much product we should make, right? So in this case, if we started with 10 grams of H2, and we want to know how many grams of NH3 we would use the molar mass of H2. From the periodic table, that is 2 times carbon's molar mass, or hydrogen's molar mass. That would be a better use. We would then do a mole to mole relationship between these two. For every 3 moles of H2, we get 2 moles of NH3. And if I stop right at this point, the grams of H2 will cancel, the moles of H2 will cancel. I'm in moles of NH3, which means I can figure out how many grams that would be by using the molar mass here of NH3. NH3, which obviously has 1 nitrogen and 3 hydrogens, right? By the way, when you pull the molar mass on the periodic table, it is tradition to take how many significant figures? 4 significant figures when you pull it off the periodic table for the molar mass. So that's going to be 17.03 grams per mole, which we will use as a conversion here per mole. That mole is going to cancel. That will get me 10 times 2 times 17.03 in my made up here. Let me actually punch it in correctly. That probably would be a little bit more helpful. Let me try that. Divided by 3. Oh, give me something like 0.672 grams of NH3. That means if I throw into here 10 grams, I really should get out 0.67 grams of NH3 based on sig figs, which is probably this guy right here. I think I squeezed a decimal point next to that 0. If I throw in 10 grams, everything goes great. No side reactions. I'm not a klutz and I drop everything on the floor. I should get out 0.67 grams of that NH3. That is also known as what? What type of yield? Starts with a T and it's very theoretical. That would be it. Yeah, so that's the theoretical yield there, yeah. I think that's what they call that. That's the theoretical yield. We use that with percent yield, right? Which is the percent yield is our actual, right? What you actually get divided by the theoretical, which you get from the equation or calculation from the equation times 100%. Do we want a low or high percent yield? Yes, you do want a high percent yield. Do you want over 100% yield? Is that a good thing? That's not. That means you really screwed up pretty much, right? So, under 100 is good. Not under like 20. That would be not so great. And sometimes when we do stoichiometry, the other thing that's important, right, is our friend limiting reagents, right? Or sometimes referred to as limiting reactants, whatever you want to call it. Yeah. So when you do that, you do have to do an additional step in your stoichiometry calculation, right? You got to figure out your limiting reagent. There's many ways you could do that. I would say nowadays probably people are taught just to do 2 separate calculations, and whichever one gives you the smallest amount is your limiting reagent. That's such a waste of time. But yeah, that's the way you could do it that way. Yeah. You also could do a simple little calculation where you figure out, do you have enough of one reactant to use up the other reactant, which is another common way of doing it. Or you could do it probably the right way that nobody teaches in Chem 50, which is what the type of calculation we'll do in here. I can actually use like an ice table or something like that to do that as well, which is very useful. So there are multiple ways that you could do that. The way that you know that it is a limiting reagent problem, how do you know you should calculate a limiting reagent or figure it out? How do you know it's that type of problem? Yeah, so it's not necessarily just 2 values, but you have enough information for all the reactants to really get to the moles. So if you have enough information given to you about the reactants, which is a lot of times 2 pieces of information, if you have enough information for the reactants to actually calculate the moles of each reactant, then you should be doing some type of limiting reagent. Remember, stoichiometry comes with grams and moles, right? Stoichiometry comes with solutions, molarity and moles and volume. So also gas stoichiometry, right? So there's a lot of places where we do stoichiometry sort of calculations. Any questions on any of that there? All right, then that brings us to types of reactions. And there's really 3 reasons a reaction takes place. One reason a reaction takes place is a transfer of electrons, the formation of a solid, and really the formation of water. Pretty much all chemical reactions break down to those three things happening. Either you have some electrons moving, you have made water, congratulations, or you made a solid, congratulations as well. That is basically where all these things boil down to. There's really two big categories of types of reactions. There are double displacement reactions, which are the big umbrella of reactions. In a double displacement reaction, you have two ionic compounds. I'll learn the alphabet there. We'll use D on that, maybe. So ionic compounds are a positive and negative thing, right? That's a cation and an anion. They are ionically held together by electrostatic attraction, right? Opposites attract. Are there sharing of electrons in ionic compounds? Or not, right? So sharing of electrons happen only molecular compounds or covalent compounds. What happens is we get a switch of partners that happens here, right? So we do get two new ionic compounds that form. And the result of this is one of two things will happen. You'll either make a solid, which is sometimes referred to as a precipitate, a PPT. And that is a type of reaction which is under here, which is known as a precipitation reaction. And that's like something like if you take some sodium chloride plus a little silver nitrate. You will have a positive, negative. You'll get some silver chloride plus some sodium nitrate. Right? And that will form a solid, which is a white solid that is formed as based on solubility rules. As you know, right, chlorides, bromides, and iodides are soluble in everything except for lead, silver, and mercury, right? You also know that nitrates are soluble in everything, and things from group 1 like sodium are soluble in everything. Yes, so that's why those schemes get the aqueous. If things are soluble, they are aqueous. If things are insoluble, they are solids, right? And they get the solid symbol next to them. Another one of this is acid-base reactions is another one that falls under double displacement. So if you take something like hydrochloric acid plus some sodium hydroxide, which is a strong acid, strong base. Whenever you take a strong acid, strong base, you get a salt and water that is formed, right? So you get water, H plus from the acid, OH minus there from the base, and a salt in this case, which is sodium chloride, right? This is what is known as the molecular equation, right? You could also write this thing of what is happening in solution. That is a strong electrolyte, which means it'll break apart into H plus and Cl minus. That is a strong electrolyte, which means it also 100% breaks apart. Water, which is a liquid, will stay together. You also keep together anything that's a solid, anything that's gas, anything that's a weak electrolyte, right? Will mainly stay together, right? And sodium, running out of room, so I'll go underneath, sodium ion and chloride ion there. That is what is referred to sometimes as the total ionic equation or complete ionic equation, depending on who you had, maybe. When you look at the total ionic equation, you should find some ions that look exactly the same on both sides. These are what are referred to as your spectator ions, right? Spectator ions are much like the name implies, they're just hanging out watching, right? So we typically cancel these guys out on both sides, and they should, if you did this correctly, completely cancel on both sides. Leaves you the third type of equation that you might be familiar with, which is the net ionic equation, yes, which looks something like this. So under the big umbrella of double displacement reactions, you can more specifically classify a precipitation reaction, which is where a solid is formed, a acid-base reaction where water is formed, which is 2 of the 3 reasons why a reaction takes place. That is a more specific classification. The big umbrella is double displacement. As you might be familiar with, you could classify the same reaction in multiple ways, right? So depending on what you look at. Now, pretty much everybody else falls under the other big classification of reactions, which is our friends, the redox reactions. Yeah. Redox means oxidation and reduction reactions. If it is oxidation, it usually means that you have lost electrons. If it is reduction, it usually means that you have gained electrons. Some people like to remember that as the oil rig, or Leo the lion goes grr, right? Oxidizing is losing, reducing is gaining. Loss of electrons, oxidation, and gaining of electrons, reduction. You can put Leo the lion on the oil rig and he goes grr. You don't have to choose. It's okay in this case, right? Now, they always happen together, right? So somebody gets oxidized, somebody gets reduced, and that means there's also something that was referred to as the oxidizing agent or the reducing agent. The oxidizing agent is the substance that gets reduced, and the reducing agent is the substance that gets oxidized. When somebody gets oxidized and they lose electrons, do they become more positive or more negative? They do become more positive because they have less electrons, more protons, right? So you can look at what is referred to really as the oxidation state or the charge. And if you see it from reactants to products, that thing is moving in this direction, becoming more positive. It is going through oxidation if you make just a basic number line, right? Positive numbers to the right, negative numbers to the left. If you see somebody's oxidation state is becoming more negative as they go from reactants to products and moving in this direction, it is going through reduction. So that's a really quick, easy way. If you can figure out the charges, which is really the oxidation states, you can figure out who's being oxidized and who's being reduced. But it always does happen together, which means if you can figure out one, you will know the other. And the good thing about that is this is the third reason why a reaction takes place. It is those electrons being transferred from one thing to the next. Now, underneath the big umbrella of redox, you find all your other specific classifications of reactions. This is where you find your synthesis reactions, are sometimes referred to as a combination reaction, where basically 2 things make one. Yes, the 2 things come together to make one. So like a sodium plus some chlorine makes some sodium chloride. A little balancing action would be good. You could also find decompositions as a type of redox reaction. That is basically the opposite of synthesis, is where you start with one thing and you break it apart into multiple things, right? So you run an electrical current over water. It will break apart into hydrogen and oxygen in this particular case. And that's a decomposition reaction. A single replacement reaction. That is A plus B, C. If this is a metal, this has no charge, and that is a positive negative. It will come in and kick out the positive guy, because that is what metals typically make in terms of their charge. It will then gain a charge, and that guy will come out by itself. This also could be a non-metal. Non-metals typically make negative charges, which means it comes in and kicks out the negative guy in this case. Makes a new ionic compound, that guy comes out. In order for that reaction to take place, whatever is coming in needs to be more reactive than what is replacing. If it is not, then that reaction will not take place in that particular case. Also, a combustion reaction. And when we talk about a combustion reaction, the actual general definition of combustion is, frankly, that is all you need, is O2 to be present, is a combustion reaction. Most people, when they think about a combustion reaction, think about the organic combustion reaction, where you take an organic compound that contains carbon, hydrogen, or oxygen, and you react it with O2, make a little CO2 plus some water, like when you light a Bunsen burner and you get the fire that comes out and all that good stuff that happens. All these individual classifications, these are all, if you share and look at them, there are all redox reactions that are happening. There's all some type of oxidation reduction taking place. And that is why they are really under the big umbrella of those type of reactions. Any questions on that there? Now, the other really major thing that we talk about that you should know, right, is solutions, which again are these guys that have the aqueous symbol. A solution is made up of two things. That is the solute, which is the smaller part of the solution, and the solvent, which is the larger part of the solution, right? Together, they make up the solution. Is water always the solvent? No, water is a good solvent for things that are ionic or polar, right? It is a crappy solvent for things that are non-polar, right? Because they're going to separate out from each other. That's the idea of like dissolves like, right? Things that are polar and polar work good together. Things that are ionic and polar work good together. Things that are non-polar and non-polar work good together because they're all using the same intermolecular forces, be it hydrogen bonding, dipole, dispersion forces. These are all words that should be familiar to you, yes? Okay, that's good. I see nodding, so that's good. I was supposed to. But when you try to use something that's polar and non-polar, right, they don't mix because one's trying to use like dipole and one is using dispersion forces. And over a long period of time, they really cannot sort of work well with each other. So when we look at the solute, how do we know what the solute is? Well, frankly, if you have a 4.50 molar solution of sodium chloride, the name of the solution is the solute, right? And if it's ionic here, the solvent's probably water. That brings us up M, which is the very common unit of solutions, is this concentration, and that big M is molarity, right? And molarity is moles of solute per liter of solution. Our molarity is moles per liter. That means that liters is moles divided by molarity. And that means that moles is liters times molarity, right? Those are three ways that you do it. When you do a calculation involving molarity, it's highly recommended that you get rid of the big M so you can see both of the units. So if I was going to do a calculation with that molarity, that is 4.5 moles of sodium chloride per liter. And you could use it like a conversion factor and do dimensional analysis. You can flip it around the other way as well. I tell you, when most people do not get rid of the big M and just leave it and they do the calculations, they frankly have no idea where the volume is, where the liters are, or there is liters. They're kind of surprised sometimes, yes. So make sure that you use both of those units. If I have a really high molarity, that means the thing is very concentrated, right? And I have a small molarity, it is dilute, a lot more solute than solvent. Which one of these two are actually reacting when you do a reaction? You pour a couple of solutions together, which one's reacting? It is the solute, right? The solute is really the amount that's in there is the thing that is really reacting. When we do things that are more concentrated or use solutions that are more concentrated, we oftentimes will do dilution, right? And dilution is M1V1 equals M2V2. Or nowadays they go C1V1 is equal to C2V2. C is generic for concentration, V is volume. Most people use this one because molarity is the most common unit of concentration, but there are others like percent mass to mass, percent volume to volume. You know, maybe you learned some of those. This is one place where you can use the volume in milliliters with molarity because it will work out okay in both cases. When you're using molarity by itself, you should always convert the volume to liters. Yeah. So that is because if you take milliliters and you times it by molarity, do you get moles? You do not. You get millimoles. Yeah. Which is like moles, but kind of like milli of it. You know what I'm saying? So it's not in moles. So you should always convert the volume to molarity. That way, when you do this conversion, you actually get moles, which is what you're anticipating. Here, you're about 1,000-fold off of what you think it is, yes? It's okay in this formula because when you use milliliters here and milliliters here, they cancel out or use molarity and molarity. Molarity can be also thought of as millimoles per milliliter, which is those two millis cancel and you get moles per liter. So you gotta be careful with the volume when you use it. The amount of solute before and after the dilution is the same. The only thing that's changed is you added more solvent to it, right? So in a lot of cases, you added more water. When you solve for M1, that is the more concentrated solution usually. That is the volume of the concentrated solution you need to use. That is the molarity of the diluted solution. And that is the volume of the diluted solution that you're going to make. Now, if I want to know how much water I needed to add in a situation like this, how would I figure that out? You would subtract your V2 from your V1, right? Because the only difference there should be, for example, how much water you would add if you're going to do a dilution with water. Now, sometimes we do dilutions and we don't realize we're doing dilutions. So let's just say we had a table here and we wanted to put in A and we want to put in some B and we want to put in some water. So these are different molarities. And let's just say that this guy is 5 molar, this guy is 2 molar, and that is obviously water. Now let's say in test tube number 1 here, test tube number 2, we're going to put 5 milliliters of this guy. We'll do 3 milliliters of this guy and 2 milliliters of this guy. And test tube number 2 here, we're going to do 3 milliliters of this guy. We'll do 2 milliliters of this guy and 5 milliliters of water in this case. Yeah. So my question is, when I throw them all into this beaker together, both A and B in here, the concentration, which is what the bracket represents of A, right? That means molarity. What is the molarity of A in this case? Is it 5 molar? It is not, right? Is the concentration of B 2 molar? It is not, because when you're doing this, you're actually doing a dilution, right? So what happens is at this point, let's just say we put it into a test tube. I take for test tube number 1 here, my 5 milliliters of A. At this point, the concentration of A is how much? 5, right, at this point, right? But now when I throw in there my 3 milliliters of B, the volume changes, right? So whenever you add volume, the molarity changes because the molarity is moles of solute per liter of solution. That means as soon as you add more volume, the volume part changes, the molarity changes as well. So we're actually doing a dilution. And now as I dump in my 2 milliliters of water here, I'm diluting it even more. So I would need to use M1 V1 equals M2 V2. Here for test tube 1, my initial concentration was 5 molar. My initial volume was 5 milliliters. I'm looking for what it is when it's all mixed together. My final volume is found how? Yeah, these are all the components of what I put in there, right? So it has to add up the entire volume, and that is 10 milliliters in this case. Once again, here you could convert to liters, or you can leave it in milliliters, because when you do the math here, divide the 10 to the other side, divided by 10 milliliters. The milliliters will cancel and we'll be left with molarity. So it works out okay with the milliliters that are there. So in this case, we end up with a 2.5 molar. So as we mix all this together, the molarity changes, and with it all mixed together, that is going to give us our concentration of 2.5 molar. So we do this a lot in lab, right? We put a bunch of stuff into a test tube, and you oftentimes need to calculate the molarity of the actual solution after everything's mixed together, and that really is a dilution. So we do use dilution a lot, that equation. We use molarity a lot to figure out things like moles and volume that you need. So those are important things. Any questions on any of this sort of review stuff? Hopefully it is review, yes? Okay, couple of things just to note, as I mentioned before, if you